All right, this is our video for Calculus BC. Heading into the final couple days of our semester, we're going to be trying to piggyback of where we finished off today and moving into where we're going to finish in our last 2 days. So we're going to be, let's take a look here at these 4 series and intervals of convergence that we need to commit to memory. So we've looked at all 4 of these in some degree or another, so I just want to put these out here plainly that these are 4 series that we want to have memorized and available to us, and we're going to see here in the next few minutes in this video how that would be important. But let's put down the intervals of convergence here to go along with this. So maybe you remember e to the x, the interval for of convergence for e to the x is infinite, and the interval of convergence for both cosine and sine are infinite as well. But then when we get to that final series, which is the geometric series, this converges only for x values that are between 1 and -1, not including those endpoints. So like I said, we want to have those committed to memory and to be able to use those at a moment's notice. So let's take a look at the next little example here. This is just a brief way of seeing how this could be useful. We'll certainly look at others in this video. So this right here at the bottom of that page says determine the exact value of pi minus pi cubed over 3 factorial plus, dot, dot, dot. You can see all that there. It gives you this kind of this nth term as well to this particular series. The idea with a question like this would be to recognize what this series is and see that this series is really similar to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. You can see that nth term there perhaps would be -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. The idea is somewhere in here, somewhere in this process of trying to recognize what's going on, we'd hopefully recognize that this series that we're dealing with is the series for sine. And so then if we look at the question that we're actually supposed to answer, you can see that x has been replaced by pi. So this series right here would then equal sine of pi, which is, amazingly enough, 0. We could probably do some partial sums to see how this starts to kind of narrow in on 0, but the easier way would be to recognize that this is the power series for sine, and specifically sine of pi, and since we know what sine of pi is, we could arrive at that answer fairly quickly. But once we recognize it, and recognizing it being the key to recognition, having seen something many times or memorized it, whatever it might be. So let's continue this process as we look at a few other ways to use these 4 basic series that need to be memorized and what we can do with those. Okay, so power series, as mentioned here, can be differentiated and integrated, and that's actually one of the really strong suits of a power series, because a power series is simply a polynomial, and so it's very easy to differentiate and integrate polynomials because we typically just use the power rule for that. So when we do these derivatives and integrals, the radius of convergence will be the same as the radius of convergence of what we just differentiated or integrated. Sometimes, not often, at least that I've seen, sometimes the endpoint behavior might be a little bit different, but we'll investigate that as we go. So number 7 here says for the function given by that particular power series right there, question A says find the interval of convergence for f of x for this series. So we've actually done this up above. I'll do it again here real quick. This maybe will be a good review for you. But know that we've seen this before. It's going to be the limit as n goes to infinity. I'll just use the ratio test for this. So the ratio test would be x to the n plus 1 over n plus 1 times n over x to the n is less than 1. We do our canceling and so on and so forth here. We get limit as n goes to infinity. And then with the x's, we're going to just be subtracting those exponents, and so we just get x. And then I'm going to write this as n over n plus 1. I'll kind of separate it out a little bit like that. So now as we apply the limit really only applies to this part, and the limit as n goes to infinity, we can use our little trick with degree, say that the degrees are equal, therefore the ratio of the lead coefficients will be the limit. So we can see that it would be 1. So 1 times x is just x, so we'd get the absolute value of x is less than 1. And then, continuing on, we would say that our radius of convergence is 1, but our interval of convergence is going to be -1 is less than x, which is less than 1, but we got to make sure that we understand what's going on at the endpoints. So I would say for x equals -1, we would have sigma of -1 to the n over n, and that converges because that series is an alternating harmonic. And then for x equals 1, it would be sigma of 1 to the n over n, and that diverges because that is a harmonic series. So, like I said, we've done this before. I thought we'd review it. So based on that kind of reasoning there, I would say that our interval of convergence would be -1 is less than or equal to x, which is less than 1. That would be our final interval of convergence there. So B is what's new. B says find f prime and integral of f. And so I think I'll switch screens on here and we'll do that one. Okay, so I have written the power series here for f of x. Again, it's just from up above, just so we can use this here in part B. So part B says find f prime. So let's do that first. So f prime would just be the derivative of each one of those terms. So it would be 1 plus x plus x squared, so on and so forth. I guess we'll just leave it at there. We normally do 4 terms. We'll just do 3 terms here. So those are the first 3 terms right there, and it says include the general terms for both. And so one thing I want to make you aware of is that as far as finding the general term here, we could go through and try and figure out a pattern, but there's a little easier way. We could simply take the nth term that we had from above and differentiate that. So that would be nx to the n minus 1 over n, and of course the n's would cancel, so really my nth term is x to the n minus 1. So what I'm getting at here is that you can just differentiate, or here, as we'll see in a second, you could integrate that nth term to generate it as opposed to going back and trying to refigure out a pattern and write that nth term. So then if we were going to do the antiderivative of f of x, we would get 1/2 x squared plus x cubed over 6 plus x to the 4th over 12 plus ... So once again, we got our 3 terms here. And our nth term, we could try to figure out this pattern. I mean, the denominators go 2, 6, 12, and I mean, you could definitely do it, there's no doubt. Or you could just take your nth term that you're actually anti-differentiating and anti-differentiate that. So this would end up being x to the n plus 1 over n times n plus 1. Once again, all I'm doing is I'm taking this x to the n over n, and I'm just anti-differentiating that to generate my, my new nth term. Okay, so let's take a look at C here. C says find the interval of convergence for f prime and integral of f of x. So keep this in mind. We can shortcut this a little bit because we know that the radius of convergence will remain the same, but the endpoint behavior could differ slightly. Often it doesn't, sometimes it does. So let's figure this out. I'm going to use my nth term to do this. So I'm going to look at f prime here first. So I'm going to set up my ratio test, and so it's going to be the limit as, well, sorry, I guess I don't need to do my ratio test. I just got done saying that. I'll just do my endpoints here. So I know for sure that for f prime, my radius of convergence is 1. So it's going to be -1 is less than x, less than 1, with question marks here. We don't know if these are going to be open or closed. Originally the lower one was closed and the upper one was open. So let's take a look here. We've got sigma of x to the n minus 1. So for x equals -1, let's see here. It's going to be, so we get something like this, sigma of -1 to the n minus 1. Kind of interesting. I'll come back up here and rewrite a little bit. Hopefully see what's going on here. So this is really -1 to the n over -1, because if you're subtracting exponents, you're really dividing. So this is going to be an alternating series of a sort, but it appears that regardless, the terms are going to be 1. So it looks like if we started this series off, I guess we'd be starting this series off at 1, looking back on what we have above. It's just going to be, it looks like it's just going to be 1, -1, 1, -1, 1, -1. So I think this would diverge because of the nth term test. And then I think we'd get something really similar if we did the x equals 1. So this would be 1 to the n over 1. And this would, diverge once again because of the nth term test. And so for this particular series, we got diverging on both endpoints. And so I'll rewrite it over here. I'll just write -1 is less than x, which is less than 1. And you probably already saw this, but if you look back up here to what the series for f prime is, maybe you recognize that that's the geometric series, right? 1 plus x squared plus x cubed. So maybe it makes sense that this would only converge. This would not converge for the endpoints. This would just be open convergence on both. And then if we did the interval of convergence for the other one, we would see sigma of x to the n plus 1 over n times n plus 1. And so testing out those endpoints, so when x is -1, we would get sigma -1 to the n plus 1 over n times n plus 1. So this would be an alternating series, it would be, the terms would be decreasing in absolute value to 0. And so I think we would be have a closed interval. So we would say, this converges because of the alternating series test. And then for x equals 1, we would get sigma of 1 to the n plus 1. So that's definitely not alternating, but then it would be n times n plus 1 down here. And so this is essentially 1 over n squared plus n. And this is going to converge as well. The convergence would be based on probably a limit comparison test. You could maybe do an integral test, but limit comparison would be the easier one. And so we get convergence on both endpoints there. So for that integral or antiderivative of f, our convergence is -1 is less than or equal to x, which is less than or equal to 1. So just an example of how we'll have the same radius of convergence, but perhaps different endpoint behavior. Okay, so there's a lot of review in there, a little bit of new stuff. Let's do some all new stuff here next. We'll do several examples in 9.9, 9.10. So for our video here, to finish things up, we're going to just limit ourselves to the first 3 or 4 of these. That'll put us in a good spot. I'll probably do a little bit more than I need to, I don't know, just to make sure we cover everything we need, and we'll just see where we stand after our class here later on today. So the first couple things we're going to do here are going to involve substitution. I want to be clear about what this is and why we would do this. We can construct a power series using the Taylor construction. We can construct a power series for really just about any function. But I hope you would agree that it's kind of time consuming, right? It takes quite a bit of effort to come up with each term and each coefficient and build that into the construction. And so because it takes so long, sometimes there's easier ways to do things. And so sometimes using algebra, integration, differentiation, you've already seen that a little bit, or substitution might be the best way or the fastest way to create a series that we're interested in. So number one, like I said, all these are going to involve substitutions, all the ones that we're going to do here today in this video. So number one says, write the first four terms in the general term of the power series for this function right here. And we're going to include an interval of convergence. Perhaps I'll show you how this would work. But let's check it out. So what we'd be expected to do is look at this function, 1 over 1 plus x, and we would be expected to recognize that this is just a close adaptation of a series that we do know. And hopefully, because you've seen it enough, you would recognize that it's really close to this series right here, 1 over 1 minus x, which of course is the geometric series 1 plus x squared plus x cubed plus dot 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 x to the n would be our nth term there. So like I said, we'd be expected to recognize that, and so that requires certainly that we are very familiar with those series that we're supposed to have memorized. So as you can see, this series that we're supposed to find is really similar. It's only differing by a plus sign as opposed to a minus sign from before, and so we're supposed to figure out how to get there. Here's how you get there. If we use substitution, we get something like this. If I substitute negative x in place of x, then you can see, of course, that minus minus is really a plus. So whatever I do to the left side, I've got to do the exact same thing to the right side. And so what I would do here is wherever I see an x, I would plug in a negative x. So it would be 1 plus negative x quantity squared plus negative x quantity cubed plus dot 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 negative x to the n. So this, again, this sort of thinking will work for an nth term. Simply wherever you see an x, you plug in negative x, and you'll have it. So this is technically it. I'm going to clean this up a little bit. So it would be 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed plus dot dot dot. And like we've customarily done, I'm going to break the alternating element out. So it would be negative 1 to the n times x to the n. And so, yeah, we've turned this into an alternating series by substitution, and based on that substitution, we can know that we have the series for 1 over 1 plus x. And again, I want to be as clear as possible. We could certainly find this series for this particular function by using a Taylor or Maclaurin construction technique, but I hope that you'll agree it's so much easier just to use substitution here based on the fact that we already know 1 over 1 minus x. We can then adapt that to be 1 over 1 plus x by using substitution. I think I'll forego the interval of convergence here. You certainly can do that if you want. Just give you a brief hint. If you can substitute into it as well. So the original interval of convergence was negative 1 is less than x, which is less than 1. So if we just substitute negative x in there, we can then adapt this interval of convergence to get where we want to go. Okay, let's take a look at a few more. Okay, so number 2, very similar question. It wants us to find the power series for 1 over 1 plus x squared. And again, we could use a Taylor series to do this, Taylor series construction. But because this looks an awful lot like a series that we know, we would perhaps elect to use that as opposed to the Taylor construction. So again, I'm hoping that you would recognize that 1 over 1 plus x squared is very similar to 1 over 1 minus x. And I'll just reiterate this. Hopefully this repetition will be helpful for you in getting this memorized. But here it is all the way through your nth term. And so now the question is, all right, how do I turn this 1 over 1 minus x into 1 over 1 plus x squared? And I gave you the hint at the start that all of these we're going to do in this video are going to involve substitution. Later on we'll do other stuff, but for now, substitution. So pause, think about it, whatever. I'm going to go ahead and let you know what it is. If we substitute 1 over 1 minus negative x squared, then I think we'd have it, right? Because minus minus is really a plus, and we'd have what we're supposed to be finding here, 1 over 1 plus x squared. So then we could say then if we substitute negative x squared in for x on the left side, we've got to do the exact same thing on the right side. So the series now, the power series would become 1 plus negative x squared plus negative x squared squared plus negative x squared cubed plus dot dot dot. I don't know if I can fit this in. my page here, I'll go negative x squared to the n. So really, technically, that's it. I think you'll find that often getting things cleaned up will be helpful and suggest that you at least be able to do this. So this would be 1 over 1 plus x squared equals 1 minus x squared plus x to the 4th minus x to the 6th plus dot 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 plus, I'll separate out again here, negative 1 to the n, x to the 2n would be your nth term there. I think we'll pass on the interval of convergence here just in the interest of time. Let's do a couple more. Okay, same question, different focus. Write the first 4 terms in the general term of the power series for f of x equals 1 over x. And this will be an interesting one here. We'll talk about a couple of aspects as we go through this. And I think maybe we'll stop at number 4. I don't know, maybe we'll do 5. We'll see how it goes. Okay, so the idea here is, once again, we've got this, this function we're supposed to write a power series for, and we are supposed to recognize that this is really similar, at least somewhat similar, to a series that we already know. So once again, this is the geometric series. It's the only one that we have that involves kind of this fractional idea, you know, like 1 over x, 1 over 1 minus x. And so, as I mentioned before, I hinted at this, and I think it's important that I kind of give you some direction here. This will be accomplished by substitution again. We need to figure out something to plug in for x that will allow us to convert this over to 1 over x. So again, feel free to pause the video, think it through yourself. I'm going to go ahead and let you know what it should be right now. Let's remember, though, that 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus dot 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 x to the n. So the substitution goes like this. 1 over 1 minus, if I replace the x with 1 minus x, then I believe it'll be accomplished, right? Because it would be 1 minus 1, which is 0, and then minus minus x would be plus x. This is a little tougher substitution here. So again, what this means is if I substitute on the left, I've got to substitute the same way on the right. So wherever I see an x, I'm going to put 1 minus x. So this would be 1 plus 1 minus x plus 1 minus x squared plus 1 minus x cubed plus dot 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 plus 1 minus x to the n. So that's it. I think we can talk about the interval of convergence as well, but let me talk real briefly about this. Maybe you noticed this, but we have changed the centering point, right? So this series that we originally started off with was a Maclaurin series centered at 0. You can tell because they're all x's, right? It's not like x plus 2 or x minus 4. It's just x, so it's really technically x plus 0. And so then if you notice what we've done here in number 3 is we have moved the centering point to be 1. We've moved the centering point over a little bit. And the reasoning behind that is that 1 over x is not defined as 0. Right? You can't plug in a 0 there. And so because 1 over x is not defined as 0, we have to have a different centering point in order to write a power series for it. And so it just so happens that using substitution here, having a centering point of 1 is the way to go. And then as far as the interval of convergence, so of course our original interval of convergence was negative 1 is less than x, which is less than 1. So if I substitute, it would be negative 1 is less than, I'll just substitute in here 1 minus x, which is less than 1. So if we solve this, I would subtract 1 from both sides first and get negative 2 is less than negative x, which is less than 0. And then divide by negative 1. Dividing by negative 1 would flip things around a lot. It would be actually 2 is greater than x, which is greater than 0. Or more commonly written, 0 is less than x, which is less than 2. And maybe now you can see that, yeah, the centering point is 1, right? Because the interval of convergence starts at 0 and ends at 2. And so that centering point would be 1, as we discussed before. And the endpoints, I believe, here should remain the same. Although actually, I don't know. Maybe that's something we can look at in class. I don't want to take too much more of your time. No, I think the endpoints remain the same. Okay, anyhow, let's take a look at number 4 and see how it goes. All right, so number 4, hopefully you're getting kind of the hang of this at this point, so feel free to try number 4 by yourself and then see how you do with it. I'm going to go ahead and start. It's the same question, now just a different function, and so it'll be a different power series. So it says, write the power series, the first 4 terms for f of x equals cosine of root x. And so maybe you can see the substitution will be different here, right? Because cosine, that's a pretty clear sign that we're talking about a different function besides the geometric function we've been talking about. So I think we'd start off with this. Cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. And then our nth term, of course, is negative 1 to the n, x to the 2n over 2n factorial. But again, hopefully that's something you have memorized, and maybe you can see how this will come into play, because all we're going to do here is recognize that to get cosine of root x, I could just replace the x with root x. So I'll do that. So it'd be cosine of root x is equal to 1 minus root x squared over 2 factorial minus root x to the 4th over 4 factorial minus root x to the 6th over 6 factorial. And then our nth term would simply be another substitution. So it would be negative 1 to the n, and it would be root x to the 2n all over 2n factorial. You don't have to do this. I think it could be very useful, especially in a multiple choice scenario, and perhaps a free response scenario as well. I'm going to clean this up a little bit. So cosine of root x would equal 1 minus, this would just be x over 2 factorial, minus x squared over 4 factorial. Oops, I made a mistake with my minus signs there, so this would be a plus, sorry, and a plus. There we go. Minus x to the 3rd over 6 factorial plus dot 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 plus negative 1 to the n, and then oh, darn it, I forgot my 2 here. Sorry, I think I was thinking one step ahead and messed that up. So it would be root x to the 2n. So root x squared is just x, so it would be x to the n over 2n factorial. Sorry about those little oopses there. I think I caught them. Okay, so that would be a power series for cosine of root x. So I'll tell you what, let's do half of 5, and perhaps maybe we'll open with the other half when I see you next time. Okay, so number 5. Write the first 4 terms in the general term of the power series for f of x equals e to the negative x squared. So let's start off with this. Does this look like a series that we know? Of course it does. It looks like e to the x. We've seen this function several times before. So we'd say e to the x is, as a power series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus plus dot 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 plus x to the n over n factorial. So then, again, this is a substitution. So, think, how could I get e to the negative x squared? Well, I'm just going to replace my x with negative x squared. So e to the negative x squared equals, wherever I see an x, I'm going to put negative x squared. So it would be 1 minus x squared plus negative x squared over 2 factorial plus negative x squared cubed over 3 factorial plus dot 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 negative x squared to the n over n factorial. So if I clean this up a little bit, I get e to the negative x squared equals 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. And then I think I'll separate the alternating element out again, so it would be negative 1 to the n times x to the 2n all over n factorial. And so what we'll do when I see you guys next time is use this to work with integrals and see how we could use this to help us actually deal with an integral that we really don't know how to deal with yet. All right, so thanks for watching. I hope you learned what you could there. Please come to class with this stuff. pretty solid. We'll do some reviewing, as we go through the next couple of days, but you want to learn all that you possibly can from this as we look to move forward and finish our final couple of days. See you soon.